just want to go over real quickly what we observed yesterday with our sine function. So here we have one period of sine, and yesterday we explored what the parameters, what adding or subtracting a number to x or multiplying x by a number, what it does to our sine function. So we can see that we have x minus c here. So if we are subtracting a positive value, whoops, let's go back to 0. If we are subtracting a positive value, we can see that our function moves to the right. And if we are subtracting a negative value, our function is going to move to the left. So we can kind of see that horizontal movement from left or right is controlled by adding or subtracting a value to our x portion of the function. We also explored multiplying our function by a number. So here we have 1. So we're just have our regular parent function for sine. And if we multiply our x by a whole number, we're going to see that this angle, remember our x-axis is our angle theta, we'll see that angle is going to increase more quickly because we're multiplying it by a number greater than 1. So our angle is getting bigger faster, which means it takes less space to complete one period or one full cycle of our sine function. We can also see that if we multiply it by a fraction or a number less than 1, where our angle is not increasing as quickly, it's increasing more slowly, which is, we can see why it takes longer to complete one full cycle than it would, by multiplying it by a 1. So that fraction makes our period longer. So we can see in this case, the period is 5 pi instead of 2 pi. So again, the horizontal movement is controlled by numbers being added or subtracted or multiplied by our x. And we can see that our vertical values are not changing at all. So now we'll explore to make sure that our cosine function behaves the same way as our sine function when we are adding or subtracting or multiplying numbers to that x value. So here we have one period of our cosine function, and we can see that if we add a value to our x, it still controls that horizontal movement, or if we subtract another value, we will still control that movement from left or right. So if we have that positive or that negative, we can see it controls one direction or the other. And we can also see that if we multiply by a number, so if we take our cosine function and we multiply it by something greater than 1, we can see that just like sine, it compresses our function. And if we were to multiply it by a number less than 1, we can see that it stretches our function. So just like before, our angle increases more quickly with a whole number, and then our angle increases less quickly, more slowly, with a fraction, or in this case, a decimal. So we can see in both of these cases, the output values, our vertical is still the same. This, remember, our values inside the x only control that horizontal movement. So I kind of have a summary of our sine and cosine function in terms of the period. So yesterday we explored how we can describe period by subtracting the ending point and the starting point. So what we're going to do for our functions today is we're going to use these parent functions to help us determine the period. So for this first example, we have y equals sine 2x plus pi. And so to find the period, we find the place where this function starts. So we're going to set whatever is inside the function, whatever is inside sine, we're going to set that equal to the normal parent starting point. So typically sine starts at 0. So we're going to set this portion of the function equal to 0, and then we'll solve. Divide by 2, we'll get x equals negative pi over 2. So that's going to be where our function begins. And then we'll find the ending point by setting whatever's inside the function equal to our normal ending point in the parent function. So 2x plus pi equals 2 pi. So we'll solve it just the same. 2x equals pi. And we get the ending point is positive pi over 2. So to find the period, we're just going to subtract the ending point and the starting point. So we're going to say end minus start, which will equal pi over 2 minus our negative pi over 2, which will equal 1 full pi. So the period in this case would be 1 full pi. Okay, so we have our next example. We have y equals negative 3 cosine 2 times the difference of x minus pi over 4. So we know this is written a little bit different than our last function. We have parentheses around the whole expression, where here we have kind of parentheses separating our expression. We can still see whatever's inside our cosine function is what we're going to use to find that period. So just like before, we're going to set it equal to the parent function, where the parent function of cosine starts. So cosine we know starts at 0. So we're going to set this equal to 0 to solve. So we can go ahead and divide by 2 right away. X minus pi over 4 equals 0. So x will equal pi over 4. So that's where our function is going to start. And then we're going to set the ending point, set this portion of our function, the input, set it equal to the parent function ending point. So we know cosine always ends at 2 pi, just like sine. So it ends here at 2 pi, and we're just looking at the x-axis. So we'll divide by 2 to solve. X minus pi over 4 equals pi. So if we add pi over 4 to both sides, we get 1 1/4 pi, or 5 pi over 4. And again, we're finding the period, so we're taking the ending point minus the starting point. So it's going to equal end minus start, which will equal 5 pi over 4, or 1 1/4 pi. I don't really have a preference of how you write it. This is probably more commonly accepted, but I know this makes it a little bit easier to find the period. So both ways is fine. So if we said 5 pi over 4, or 1 1/4 pi minus another quarter, will give us 1 whole pi. And that's going to be the period for this cosine function.